Okay, so I didn't realize so many people who are here today were here yesterday. So you got an idea yesterday of a little bit of the history of deep learning and kind of the state of the art in what we can do with supervised learning, and then a little bit of a hint of where future problems lie and how we might address them. And today, so I spent quite a lot of time in the first part and a kind of short time in the second part. Today it's going to be the opposite. So for those of you who were not here yesterday, you'll hear an extremely fast version of what I talked about yesterday. So as not to be too boring for the people who actually were here, and then I'll spend more time on issues. Some of them are mathematical in nature, some of them are more kind of conceptual, and then I'll try to end with some sort of broad questions about how we do science and where AI is going and the influence in society, which is kind of completely different from what we talked about yesterday. Let me start with a couple of questions. So this is a slide I actually showed yesterday, but here I'm showing it first. There's a quote here from Josh Tenenbaum, who is a cognitive scientist at MIT, who said recently, all of these AI systems that we see, none of them is real AI. And what he says is that all of the systems that we have are trained with supervised learning, and supervised learning is very limited, and there is essentially no way we're going to build truly intelligent systems with supervised learning. But supervised learning still works. It's very useful. So one question I'm going to ask during this talk is, how can we do better? Like, what's missing, essentially? And this is very conceptual. It's very preliminary. Not everybody agrees in the AI community that this is the right thing. So let's start with supervised learning. I also showed this slide yesterday. Supervised learning, you have a machine. It's a parameterized function. You show it an image. You want a particular output. Let's say you want to turn on the red light and turn off the green light to indicate that it's a car. And if the machine doesn't produce the right answer, you give it the correct answer, and you adjust the parameters so that the answer produced by the machine gets closer to the one you want, okay? And then you repeat this process by showing thousands and thousands of images of cars and airplanes, and eventually the parameters of the machine kind of settle on the configuration that is capable of distinguishing cars and airplanes, including examples it's never seen before. And if you build those systems properly using deep architectures, what happens is that those systems can distinguish objects even whose appearance varies a lot, like chairs and airplanes. There's all kinds of weird airplanes as well. So what deep learning is really is the idea that you build this parameterized box as kind of a network. In this case, just a very simple cascade, but it could be a complex network of modules, each of which computes a nonlinear function, which has parameters, and you're going to learn those parameters. And so you show an example, propagate through this entire thing, tell the machine what output you want, and then figure out in which direction and by how much to tweak all the parameters of the machine so that the output gets closer to what you want. Now, the next question you can ask is, what do you put in those boxes? And the kind of classical approach, which is neural nets, is to say, we're going to build this network as a succession of two types of modules, two types of operators. First operator is a linear operator. So you imagine that the internal state of the machine, so these are the multiple layers of the machine, and if the internal state of it is kind of a vector, the input is also a vector. You can represent an image as a vector of pixels, or a text as kind of a sequence of vectors representing words, or you can also represent audio signals. So let's imagine this is a vector. It might have some internal structure, but let's forget about that for now. So you apply a linear operator, which means you take the vector, multiply it by a matrix, and that's one type of module. And then the second type of operator is a pointwise nonlinearity. And in modern neural nets, we use this very, very simple and non-differentiable, or at least not everywhere differentiable, function called a ReLU, which is just a max of x and 0. So you apply this function to every component of each vector. Okay, and you alternate those two operations, linear operation, pointwise nonlinearity, linear, pointwise nonlinearity, etc. That's a basic neural net where you can stack as many stages of this as you want. Now, you need nonlinearities in between the linear operators, because if you don't have a nonlinearity, then you can merge those two linear operations together, and it's just another matrix, right? So you need nonlinearities to actually do something. A linear operation doesn't do anything, essentially, for a pattern recognition person. A linear transform doesn't do anything for you. It's kind of sad to say for mathematicians, but that's true. So So the fact that this is not everywhere differentiable might actually also kind of make some mathematicians kind of pull their hair out, because the first thing we're going to do is compute the gradient of some objective function with respect to the parameters. We can't really compute a gradient because that's not really differentiable. So what we're going to do, we're going to call it a subgradient. And so if you do a global replace in my talk of gradient by subgradient, then you can be happy. But technically, it's a subgradient. Okay. So essentially, the model of learning is really simple. It's just function optimization. So you have a collection of examples, and for each example, you have an input and a desired output. You measure the discrepancy between the output you want and the output you get through an objective function. And we're basically going to optimize the parameters of this learning machine through something called stochastic gradient descent. People in optimization, actually, Stephen Wright, at a recent workshop last year at IPAM said we should not call this stochastic gradient descent because it's not a descent algorithm. Sometimes it goes up, so let's call it stochastic gradient optimization. Unfortunately, that train had left the station, so we still call it SGD. And the basic idea of SGD is you show one sample. What you really want is minimize the average over a whole bunch of training samples of this objective function. So what you could do is compute the average of this objective function, then compute the gradient of this objective function with respect to the parameters, and then make an update. But that turns out to be very slow and inefficient. The more efficient version is you just take one sample, compute the objective function, compute the gradient of this component of the objective function with respect to the parameters, just based on this one sample, and make an update of the parameters. So what you get is a very noisy estimate of the gradient just for that sample. And the average of the gradient is going to be the gradient of the average, so it's okay, things worked out. Turns out it's hellishly complicated to show that this SGD algorithm actually converges. And being an engineer, I don't get encumbered with those kind of difficulty, but I leave that to my dear colleagues like Léon Boutou, who's spent a number of years trying to figure this out. And you get this kind of trajectory, and so imagine this is an objective function. These are the lines of equal cost, and the optimization kind of goes more or less randomly. Here, it looks quasi-periodic because the samples are shown in a constant order, so there's a little bit of periodicity in it. So it's very simple. It's just gradient descent, essentially. Take a parameter in your system and replace its value by itself minus some step size times the partial derivative of the objective function you want to minimize with respect to that particular parameter, and you do this for all parameters simultaneously. Of course, you can be a little smart about how you compute this, but people use very simple schemes. So when, of course, what people came up with in the context of machine learning in the 80s is the idea that you can compute those gradients very efficiently when you have a network that's built as a graph of differentiable modules or semi-differentiable modules. And I'm not going to go into the details of this because I'm sure a lot of you have seen this before. This is called the backpropagation algorithm, and it's basically just a practical application of chain rule. So if you know how to compute the output of a module in your network as a function of its inputs and its internal parameters, then if you know the gradient of some objective function with respect to the output of this module, okay, this presumably comes from the top, then by multiplying this vector by the Jacobian of this box, which is the matrix of all the partial derivatives of every output with respect to every input, then you get the gradient of that same objective function with respect to the input, and that's just an application of chain rule. So that's what we have here. The gradient of some objective with respect to the input of a module is equal to the gradient of the objective with respect to the output of the module multiplied by the Jacobian matrix of the module with respect to its input. There's another Jacobian matrix of this box with respect to its parameters, and that's what gives you this green vector here. So by backpropagating signals all the way through, you get all the gradients of the objective with respect to every parameters in the system. And that's the backpropagation algorithm. Historically, people who first figured this out were optimal control theorists in the 60s. And they used this for basically not for learning, but for figuring out the control law for optimal trajectories to shoot rockets and stuff like that. So where the function that would be implemented by the box would be the dynamic equation of what's the state of the rocket at time t and the state of the rocket at time t+1. And this cost function would be there would be a term at every time step, which would be the energy spent, and then an ultimate cost function, which would be the distance to the space station or the moon or whatever, the orbit. And then essentially by backpropagation, which in the context of optimal control is called the adjoint state method, you would control you would figure out the control law essentially. So it's kind of like machine learning with a single learning example essentially. But then it took until the late 80s for people in kind of machine learning and neural nets to figure out that they kind of rediscovered this. It's just chain rule, but to realize that it can actually work took all that time, and it took some time to actually make it work in practice, as simple as it is. And so that didn't really become mainstream until the late 80s. And then it was popular until the mid-90s, and people kind of abandoned those techniques again for another 10 years, and they kind of popped up again in the mid-2000s. All right, so what deep learning is really is a way of essentially designing architectures of this type by having a catalog, if you want, or menagerie of different types of modules of this type, linear modules, pointwise non-linearities, and all kinds of different things, and assembling those modules into graphs, and then you get automatically the differentiation. And then you have to figure out for a particular problem or class of problems, how do I assemble those modules so that I get something that works well with relatively few training samples. So a particular example of this, of course, is convolutional networks, where basically the idea is that the linear operators that I was talking about, instead of being full matrices, are replaced by convolution. So convolution, you can think of it as kind of a circular band matrix that has kind of shared coefficients in it. But more concretely, a convolution is you take an image, you take a patch from the image, you compute the dot product of this patch with a bunch of coefficients, which is a convolution kernel. You record the result in the output, and then you take this little patch window and you slide it over the image, record the results in the resulting output, and that's a discrete convolution operation, essentially. So a convolutional net has an input, a bunch of convolution kernels that will produce, each of them will produce a feature map, and the coefficients here of those convolution kernels is what is going to be learned. And then there's a second operation called pooling, which I'm going to go into in just a minute, which reduces the resolution here and also has some non-linearities in it. And then again, convolutions here, this map is obtained by convolving these maps with multiple filters, summing up the result, passing the result through a non-linearity, and then again there's pooling, subsampling, reduces the resolution again, convolutions again, etc. So you can stack multiple layers of this. The reason for this inspiration originally is from biology, but the reason really comes from the fact that we want sort of representations that are a little bit invariant to distortion. So we want to be able to train the system in such a way that when we shift let's say a character, if you want to do character recognition, here the character shifts by, 4 pixels. This guy also by 4 pixels. This guy by 2 pixels because it's subsampled by a factor of 2, and this guy by 1 pixel. And as you go up the layers, things shift less and less. And what that means is that you have representations that are more and more kind of robust, if you want, to kind of irrelevant changes on the input. So this worked really well. In the 90s, we deployed character recognition systems, phase detection systems, etc. But there was a lot of opposition from people who are a little bit sort of theoretically inclined, if you want, because the mathematics of like how do you come up with this? You pull this architecture out of thin air. Perhaps it was inspired by biology, but what is the mathematical justification for it? And can we have bounds from learning theory or statistics that will show that the system will generalize? And so in 1995, which is the period where neural nets were starting to decrease in popularity in the machine learning community, there was a bet. So this was at Bell Labs. I was at Bell Labs at the time, and this was my department head at Bell Labs, Larry Jackal. And this is Vladimir Vapnik, very famous theoretician of learning, father of statistical learning theory. And the bet says, Jackal bets one fancy dinner that by March 14, 2000, so 5 years hence, people will understand quantitatively why big neural nets working on large databases are not so bad. Because experimentally, they were working really well. And understanding means that there will be clear conditions and bounds. Vapnik bets one fancy dinner that Jekyll is wrong. So Vapnik was the inventor of super vector machines, which were kind of well theoretically justified methods, kernel methods. There was a lot of beautiful math to do around it. He was annoyed by the fact that those kind of messy models kind of worked better than his beautiful math. And so there was this bet. But if Vapnik figures out the bounds and conditions himself, then Vapnik still wins the bet. So this was a thinly veiled stratagem by Larry to kind of convince Vapnik to actually work on the theory of neural nets. He failed. There was a second bet. Vapnik bets one fancy dinner that by March 14, 2005, no one in his right mind will use neural nets that are essentially like those used in 1995. Jekyll bet one fancy dinner that Vapnik is wrong. And so it was signed by Vapnik, Jekyll, and I was the witness. Not completely unbiased, I have to admit, okay? There was no dinner in 2000, so Larry Jekyll lost this one, Vapnik won. But Larry Jekyll won this one because in 2005 was actually just about the time when neural nets were starting to become a little more popular in the machine learning community. And we use them for robotics and stuff like that. So that's the dinner in 2005, and this is Léon Boutou, who is a bit of a neutral persona here in this bet. And since they each lost one half of the bet, they split the bill, and Léon and I just enjoyed the dinner. So in the mid-2000s, I kind of stopped working on machine learning between like 1996 and 2002 roughly, and started working on it in 2003 when I joined NYU. In fact, a little earlier when I joined NEC Research Institute, and started working on robotics, and I showed some of that stuff yesterday, so I'm not going to spend too much time on it, but this was some demonstration that those techniques could be used for things that people like DARPA would be ready to pay for, which at least was a good idea. So since most of you have seen this video before, I'm not going to spend too much time on it. And that spurred a lot of interest in self-driving cars and various other applications, semantic segmentation, which is a very important task now in computer vision. My computer is still has some trouble digesting this video. So it spurred a lot of interest from companies working on self-driving cars like Mobileye, like NVIDIA, like a bunch of others, that all of which now use convolutional nets essentially as a way of interpreting the images. Where many of us are aware of that, what happened in 2012, 2013, when our friends at University of Toronto managed to implement a large convolutional net on a GPU card very efficiently, and were able to train a large convolutional net on the ImageNet dataset, and basically got very, very low error rate, much lower than previous methods. And what we've seen is a flurry of innovation in terms of what kind of architectures to put in those systems. And the reason why people work on this is because there is a huge commercial interest in actually making those systems work for recognizing images. There's a huge amount of compute cycles that are spent processing and recognizing images by companies like Facebook, Google, and Microsoft, and just about everybody, Amazon. So there's a lot of pressure for optimizing those architectures, training them efficiently, reducing their memory footprint, reducing the amount of time it takes to run. And there's a lot of work on companies working on special purpose chips so that those things can run on smartphone, can be put in cars, eventually will be in your vacuum cleaner and every toy you buy. And so there are right now chips that are just about to come out that are capable of 1 to 10 tera operations per second, where an operation is basically one of those multiply accumulate that you need to do for neural nets in low precision in a chip that consumes less than 1 watt. So that means you can have it in your pocket, and it can, if it consumes even less than 1 watt, it can run all the time. So That's kind of a very interesting development for me, because the first few years I was at Bell Labs, we actually worked on neural net chips, you know, which some of which were somewhat practical, but not entirely. I mean, they were never commercialized. So there, you know, a lot of innovation in the type of architectures. This is a particular type called ResNet, and another one called DenseNet. This one comes out of Microsoft Research Asia, although the gentleman who came up with the idea is now at Facebook. And this one came out of a collaboration between Facebook and Cornell. And this is, you know, similar to what's used in production at Facebook for kind of recognizing images. So the state of the art in computer vision now is that you can run essentially a convolutional net on a whole image. So the convolutional net doesn't produce just a single output, but produce one output for every framing of a window on the input, if you want. So the output itself is convolutional. And there are those networks that produce not just a category, but also a kind of pictorial representation of the object that they just recognized. And that allows those systems to do what's called instance segmentation, which is a type of semantic segmentation where you don't just label each pixel with the category of the object it belongs to, but with the identity, you know, the instance of the object that it belongs to. So, you know, this pixel and that pixel both belong to a person, and, you know, you have to identify the fact that there's a boundary between two people here to make the distinction between this person and that person. So this neural net produces an output which is, you know, contains the outline of every object it recognizes, and by basically, you know, a kind of a, you can think of it conceptually as a sliding window, although it's all computed in parallel. It's very simple conceptually. It's just a large neural net. And so I showed some of those results yesterday. You get some pretty amazing results. You can do key point detection on bodies and identify the body pose. And this, you know, beats some record on a standard data set for this. In fact, this whole platform that allows systems to do object recognition, detection, localization, masking, etc. We call this Detectron, and it's open source, and you can just download the code here and run it. It's all C++. It's a bit of Python, but it kind of gives things like this. There are pre-trained models, and you can play with it and use it for whatever research you want to do. Let me skip ahead a bit. Convolutional nets can be used in all kinds of situations. Let's see. Right, so just very quickly, there's, I think I mentioned that yesterday, but I'm not sure. Well, that's interesting. All right. So one thing we use a lot at Facebook for experimenting with this is a framework called PyTorch. So PyTorch is a deep learning framework. It's basically a Python, you know, it uses Python, and it has a library for deep learning, and it allows you to essentially write a program. You have to write it in a particular way, but it's not very constraining, like a numerical program. And PyTorch automatically generates another program that computes the gradient of that program, of the output of that program, with respect to parameters that you define in advance. And so it's very convenient, not just for machine learning, but for all kinds of stuff, right? If you have, you know, some physical model of a process, you can basically write a simulator for your system and then automatically get gradients of whatever result is produced with respect to parameters, and so that you could do, you know, parameter identification, system identification, etc. So, you know, this model of you know, that is motivated by deep learning, I think is more general. We've heard a couple of talks this morning at the workshop on new methods on deep learning by Kyle Kramer, who's a colleague at NYU, on basically, you know, reducing, you know, having some differentiable form of, you know, quantum electrodynamics, for example. So you could sort of identify parameters of physics, you know, from the result of experiments by fitting those parameters, you know, back propagating through the system. So, you know, maybe that will lead to a new way of doing science. Not entirely clear, but, you know, there's a hope. There's people who write things on top of, have written a thing on top of PyTorch called Pyro. So these are people at Uber, and they're very fond of what's called probabilistic programming. So essentially it's the idea that you have a learning machine that instead of manipulating multidimensional arrays to represent its state, it manipulates distributions. And so, you know, it adds a level of complexity, and, you know, you can do things like sampling and variable inference and things like that for those systems. But that also is useful for a lot of applications. somehow. Okay. I'm not sure why. Okay, here we go. So a lot of applications, of course, very wide in healthcare, in transportation, in all kinds of stuff that we're going to see over the next few years. But I want to come back to this notion of differentiable programming. So, to some extent, deep learning is dead. I don't want to say it this way, but really I think what's going to come next is this notion of differentiable programming, which is a bit more general than sort of the pure deep learning. And the difference between pure deep learning and differential programming is that in deep learning, the graph of operators that you define is static, it's fixed. It's a convolutional net, for example, for recognizing images. Whereas in differentiable programming, the graph of operators is defined by a program that is data dependent. So depending on what you feed the system, the graph that will be instantiated for that particular input might be different. So you can imagine that this is very useful if you do natural language understanding, because the input sentence might have variable length. Okay, so necessarily, oops, what did I do? Oh, that's nice. So necessarily, the graph that you're going to connect to it is going to have a variable structure. But if it's just varying the size of a recurrent net, it's easy enough. What you'd like is something more general, where you can just completely just write a program that computes a function and then automatically get the gradient, regardless of how complicated the program is. As long as it's it computes a continuous function. If it's not continuous, then you might run into trouble trying to optimize. So the idea for this comes out of work. I mean, it goes back a long time, but it comes out of work, more recent work that came out a few years ago, 3-4 years ago, where people started kind of building computers, if you want, out of neural nets, so differentiable computers, right? So you could think of a neural net, like a recurrent net, for example, as kind of an automaton, right? You feed it an initial state, and you can kind of the network produces a new state and then feeds it back to its input and then kind of iterate for a while and then produces an output. That's a finite state automaton. It's a continuous form of an automaton, if you want, right? Very simple dynamical system. But what you'd like to have is something like like a computer, basically, where the system can access memory and then read things from a working memory and write things to it. And those are called memory augmented networks. There are several particular instances of it. Something called memory network, stack augmented recurrent nets, neural Turing machine, differentiable neural computers. Those two are from DeepMind. Those two are from Facebook. There's kind of a bit of a common interest there between Facebook and DeepMind, actually. And there's also interesting work at Microsoft and various other places in this context. So stack augmented RNN was proposed by Armand Jolin and Thomas Mikolov, and the idea there is that you have a recurrent neural net they can push vectors on a stack, and it's kind of a soft stack. So it's got a coefficient. Basically, the top of the stack is the vector you push on it, but there's some of it bleeds at the bottom, and some of the bottom of the stack kind of bleeds to it. So it's kind of soft. So you can backpropagate through this operation. And the idea for this is that if you want to do something like parsing a sentence, or making sure parentheses are balanced, or things of that type that you do with computers, you need a stack, right? A stack automaton is really what you need. So that's kind of the idea behind this. There's the end-to-end memory network, or weakly supervised memory network, which is basically a recurrent net augmented by a circuit that looks like a soft RAM. It's basically like a RAM. It behaves the same way, but it's kind of soft. So, it's not logic. It's kind of, soft responses. And it's sort of, various other architectures I'm not going to go into. So this is what a soft RAM looks like. Basically, you feed an address. So an address is a vector. You compare this vector with a bunch of key vectors, which are essentially addresses. So this looks more like a hash table, really, than a RAM. But if you have a whole bunch of vectors here, that looks a bit like a RAM. So you compute the dot product between the address inputs and each of the vectors here, which you can think of as keys. And then you take the result and you plug them through a softmax. So a softmax is basically a Gibbs distribution, something that takes the exponential of the dot product between the input and the keys, and then normalizes by the sum. So you get a bunch of numbers between 0 and 1 that sum to 1. coefficients, and you use them as coefficients with which to linearly combine the values that are in the memory. Okay, so if one of these guys matches that vector exactly, the score here is going to be close to 1, or the product of the norm of the two vectors. And if the other ones are orthogonal, they're going to be close to 0. You feed to the softmax, and this score is going to be much higher than those. And so this guy is going to, what you're going to get on the output when you do the weighted sum is basically just this vector, and these guys are going to more or less disappear. Okay, so it's a soft RAM, really, or a soft hash table. And you can backpropagate gradient through this. So if you have the access to this memory as an operation, as part of producing an output, then you can propagate gradient through it and then train the machine to adjust those vectors, or even adjust this vector so that whatever address the system that produced it feeds it is actually appropriate. So for example, if you want to build a system that answers questions, here is an example of the end-to-end memory network. Actually, the first author of this paper is here at the workshop, Saina. I don't know if he's in the room. He's heard this 100 times, so he probably isn't. But Saina Sukhpatar, he's a PhD student at NYU who is just about to graduating. So let's say you want to answer questions. So you show a question to the system. So first, this is a type of memory network where the act of writing into the memory is actually done in advance. So you get the machine to read a piece of text, and you encode this text, each sentence of the text as a vector, and you store each of those vectors in one of those memories, okay? And the key is actually the same as the content, so there's no difference between the two. So that's how this encoding is done. So you get the machine to read the text, and it stores each sentence as a vector of a key and a vector for the value. And now you want the machine to answer a question. So you feed a question to the system in the form of a vector. There's various ways to do this, and you can train this as part of the whole system. And you have it produce a vector with which you're going to address the memory. The memory is going to return a vector, and this goes through a couple of layers of a neural net, and you add the vector coming from the memory to the one coming out of the neural net, and you repeat the process. So you get, in this case, 3 hops, 3 accesses to the memory. And then the result goes through another couple layers of a neural net and then produces an output vector which you interpret as an answer. And when you train the system, you give it the correct answer. And if the answer that it produces is incorrect, then you backpropagate errors all the way through and adjust all the parameters, including all the things inside here, not the memories because they are kind of fixed, but so that the next time around the answer is closer to the correct answer. And surprisingly enough, that actually works. So what you have here is a little computer that is allowed to go through 3 cycles of reading from the memory, if you want, and kind of operating on it. So I showed yesterday a short example of a machine reading a very short version of Lord of the Rings and then being asked, where is the ring, where is Bilbo? But it can do very simple inferences, like here's an example. Sam walks into the kitchen, Sam picks up an apple, Sam walks into the bedroom, Sam drops the apple. Where is the apple? And the answer is bedroom. So you have to kind of combine several facts here to be able to answer that question. So our Jason Weston and his collaborators at Facebook kind of come up with a series of 20 different types of questions of this type, and each of which has different numbers of supporting facts that are necessary to answer the question. And those memory networks can solve 18 or 19 of those types of questions. And there's sort of more recent versions of memory type augmented network that solve all 20. So it's made progress in the last 4 years. Now the question of marrying machine learning with reasoning goes a little further than this. This is an example where what we'd like to do is get machines to answer complex questions that require a little bit of reasoning. Like, is there a matte cube that has the same size as the red metal object here? So you kind of have to look at the picture and figure out what's where. And this is where this idea of dynamic graph and differentiable programming comes into play, because this is an example where the graph of operators that is being used to compute the answer. For example, here the answer to the question, are there more cubes than yellow things? to answer this question, the system has to read the question, encode it in some ways into a vector, and then run it through LSTM, which is a particular type of recurrent nets, and produce a representation of a graph of operators whose, when we propagate a signal to it, will actually compute the answer, right? So we have a module like a convolutional net here that extracts features from the input, and then another module that filters the yellow object, another one that filters the cubes, one here that counts, another one that counts, and one that compares the two, and then you go to a classifier, and you tell the system what the correct answer is, you backpropagate the gradient, it trains the function implemented by each of those modules, it trains the convolutional net, and if you're lucky, and it's a little difficult to backpropagate through this because it's discrete, so you have to use tricks, kind of perturbation type learning here called reinforce, to train those LSTM to do the right thing. But amazingly enough, that actually works. So you can answer fairly complex questions there of this type. So that's the, I think we're going to make a lot of progress in this idea that the network kind of produces dynamically its own structure. You think that, it's a bit what we do when we face a new situation. We kind of configure, all of our attention is focused on solving this particular problem, and we kind of configure our frontal cortex to kind of think about the situation and kind of model it and answer that question. And perhaps the reason why we can only do one task at any one time and we have to concentrate on it is because we have one piece of hardware that can do this in our brains, and we have to do this consciously. There's a lot of tasks when we learn to do them, like we learn to drive, we have to completely concentrate on that task. It sort of mobilizes our entire frontal cortex and everything else in our brain. But as we get more familiar with it, that behavior gets compiled into kind of a subconscious level of our brain, and we can drive without thinking about it, and we can talk to our neighbor while driving, at least for some of us. Not everybody actually can do that. And so there's this process where, there's this very deliberate process of kind of, building a special configuration of our brains to solve a particular problem, which, if we do it often enough, kind of gets compiled into some sort of automated subconscious process. That's a kind of interesting question for how we learn. Now, another extension, which some of you who go to the workshop probably have heard a lot about today and yesterday, and perhaps again in the next few days, is the idea of spectral networks and convolutional nets on graphs. I'm not going to go into the details of this, but it's a very, very cool set of ideas that I think opened a Pandora box of possible applications of deep learning to all kinds of domains where we didn't think a priori they were useful. And we had an amazing talk this morning, first talk at the workshop, about computational chemistry using those techniques. So the idea is that when the convolutional nets I showed you, they apply to data that comes to you in the form of an array, in either a single-dimensional array, two-dimensional array, three-dimensional array, four-dimensional array, but it's basically an array of numbers, right? But you can think of, let's say, an image as being an array of numbers. You can think of it as a function on a graph, and the graph is a grid, where each pixel is a node, which is linked to its nearest neighbors. And the reason why you would put a link between neighboring pixels is because the values of neighboring pixels are likely to be correlated, right? In natural images, neighboring pixels are likely to have the same color. So over a collection of lots of images, you'll get correlations between neighboring pixels. And that correlation kind of goes down as you increase the distance between two pixels. So there is a natural kind of local graph structure to pixels, right? So one question is, can you define convolution operations on functions on irregular graphs? And the spectral graph theorists in the room say, of course you can. What you do is you compute. So a function on a graph is basically something that gives you a vector at every node, for example. And you can compute the graph Laplacian, which you can think of as a big matrix, whose dimension is the number of nodes in the graph by the number of nodes. And it's something that tells you kind of, it's a bit like a Laplacian operator, so it gives you the value at one node minus the average of the values in the surrounding nodes kind of thing. So if you take a function on a graph, multiply by this graph Laplacian, you get this kind of edge enhancement, if you want. Now, it turns out a transformation into the eigenspace of this graph Laplacian operator is actually the definition of Fourier transform. So you can define the Fourier transform over functions over irregular graphs as the transformation into the eigenspace of the graph Laplacian. And in Fourier space, a convolution is a pointwise, is a diagonal operator, right? It's a pointwise multiplication. So what that means is that you can perform a convolution in that eigenspace of the graph Laplacian. I mean, you can perform a pointwise multiplication in the eigenspace of the graph Laplacian, and that would correspond to a convolution over the function on this irregular graph. So imagine that the data you have is a molecule. Molecule is a graph. You know, it changes. The graph changes for every new molecule, and the local function is the identity of the atom that you have at each site. You could imagine representing this in kind of a normalized way. So there's sort of differing opinion about really whether this representation is useful. Leo Gibas, who is sitting here, has been working on this kind of stuff and says you're going to get sort of unstable representation if you just use this. So there's all kinds of techniques to kind of deal with this. Michael Bronstein also has worked on a lot of representation, Joan Brunat, Arthur Schlam. So there's a lot of interesting, Xavier Bresson, there's a lot of interesting work in this area, and this is a big opportunity, I think, for people coming from applied math, because, when you start talking about, eigenspace or graph Laplacian to computer scientists, starts tuning out usually. So, so I think that it's full of opportunities. Now, here is another mathematical conundrum, which is that deep learning breaks some basic rules of statistics. The networks I showed you, the convolutional nets, you can train them with, say, 1 million samples, but many of them have hundreds of millions of parameters. Now essentially you're doing curve fitting, right, with 100 million parameters, and you only have 1 million training samples. How can that possibly work? Every textbook in statistics would tell you that can't possibly work. You're going to overfit. And those systems overfit like crazy. There's a few papers that show that you can train a large convolutional net on ImageNet with completely random labels, and we completely nail the training set. Of course, it will not work at all on any test set because that makes no sense, but it will basically learn the training set very well. Those things have an enormous capacity. So it's kind of a mystery. There's some sort of built-in regularization in those systems that we don't quite understand. Another question is why doesn't deep learning get trapped in local minima? So the one reason why an excuse that people gave themselves to abandon neural nets in the 90s was to say, there's no proof of convergence because the loss function is non-convex and you're going to get trapped in local minima, and I'm going to get scared because I never know if it's going to work or not. Now, in practice, you train a neural net, it works every time, and it works to the point that the performance that you get at the end when you train it is almost always the same. You get a very different solution, a very different point in parameter space, but it works always more or less the same. What that tells you is that whatever minimum you find, they're all more or less at the same energy level, if you want. And how is that possible? So I worked with some colleagues, a few students, a postdoc, and Gérard Benarous, who is the former director of the Courant Institute, who is a random matrix theorist. And we came up with this idea. The paper has a huge amount of approximations which are probably wrong, but it's interesting to think about it. It's the fact that if you think of one of those classical neural nets as a bunch of linear operators with a ReLU, you can think of the ReLUs as kind of a switch that turns on, and it's basically the identity function, or turns off, and then it's 0, right? So think about a single path in a neural net. The contribution of this path to the output is going to be the product of the input multiplied by all the weights along the path, assuming that all the ReLUs along the path are all in the linear region. And every path is going to contribute linearly to the output to the extent that the path is activated. If any ReLU on the path is 0, then the path is going to be inactivated. This is kind of the path integral theory of neural nets, if you want. And to give you a little bit of a intuition for what those loss function looks like, let's take a very, very simple neural net, just one input, one hidden unit, one output. and just one weight, and it's completely linear, and it minimizes mean-squared error, and it computes the identity function. You train it to compute the identity function. So the solution space is set W1 to some value, and set W2 to 1 over this value, and you get the identity function, right? And so the solution space is a hyperbola, and the cost function, if you use least square for the error, is something of this type, which, is a function of this type where you have sort of fourth degree polynomial in this direction, another fourth degree polynomial in that direction, a saddle point here at 0, 0, and a hyperbolic solution space. And it's degenerate. The solution space is degenerate. And as you increase the size of this network, if you ask it to do the same function, the degeneracy of that solution space increases. There's more and more and more dimensions where you can move, and it makes no difference to the output. You're still in the solution. And it multiplies the number of dimensions of the saddle point because you can break the symmetry in all kinds of different ways, right? So let's go back to this picture of this graph of this thing here. So the input-output function of this network is the sum over all the paths of the product of all the weights along a path multiplied by a coefficient that indicates whether the path is active or not. So it's something like this. The output is equal to the sum over paths of a variable that indicates whether the path is active, multiplied by the product of all the weights along the path, multiplied by the input. And, the input, which is the source of this path, right? Now, what you're interested in really is a loss function, and you can write certain loss functions in terms of a value as well that involve the learning rate, like a hinge loss is one of those, for example. And after a little bit of hocus pocus, which is very simple, you get that the loss function is basically of the same type. It's again a sum of a path of some coefficient, which is now not just 0 or 1, but could be another value. It depends on the input, multiplied by the product of all the weights along this path. And now you can make a horrible, ridiculous approximation, which is kind of the perfect gas theory of neural nets, where you assume that all those paths are independent, so they don't actually have overlapping coefficients or anything, or states, and that this coefficient is independent of the weights, essentially. So it's just a function of the distributions of the inputs and outputs. And of course, it's not true. But if you make this independence assumption, then that becomes a polynomial of degree k, where k is the number of the number of layers, with random coefficients. And it turns out there are theoretical results on the distribution of critical points of this kind of function. At least that's what Gerben-Arous tells us. So what you have in particular is that you can figure out the distribution of where are the local minima in terms of energy level. And basically all of them are almost at the same energy level. They're called the floor, essentially. There's a few that are below, which are the global minima, the global minimum. But most of them are all within a very narrow band. And then there is an exponentially small number of them that are higher. And what that means is that the probability of getting trapped in a high local minimum is extremely small. The probability of the minimum you'll find are almost certainly within this floor. And you're never going to be able to pass through that floor to find the global minimum, but you don't care anyway. So that's kind of interesting theoretical results. I'm not going to delve on it, but I think there is a lot of better math than this to do about this to understand really the geometry of the objective function in neural nets. And perhaps geometers might be interested in this. It's very difficult to kind of build an intuition for a sort of high-dimensional, the geometry of high-dimensional manifolds of this type. And there are people who are in the, build a career on this who might be helpful in kind of helping us understanding this. There is also empirical results that show that if you train a neural net and you get twice and you get two different solutions, and then you try to draw a straight line between those two solutions and ask, can I go from one solution to the other in a straight line? You can't. It kind of goes up, the energy goes up a little bit. But then you ask the question, if I bend the path a little bit to go from one solution to another, can I go from one solution to the other without going up in energy? And the answer is usually yes. There's a paper by Yoshua Benjo about this. What that means is that the solution space is very degenerate and perhaps completely connected. We need someone who understands something about level sets, right? Okay. So let's talk about so I talked a little bit about unsupervised learning yesterday, about the necessity of it, and the fact that, common sense is the ability to fill in the blanks, predict the future from the past, predict everything that you don't directly observe, that you might eventually observe, and that way building models of the world. So to make this idea a little more concrete, if my brain is trained to predict what I'm going to observe next, and I happen to move my head 20 centimeters to the left, or in this case 50 centimeters, the best way to predict what the view is going to look like for my brain is to kind of abstract the notion of depth, right? We're not born with the idea that the world is three-dimensional and there is such a thing as depth. But if our brain trains itself to figure out how the world is going to change when we move our head, the best explanation for that is depth. If we have some representation of depth, then we can make this prediction real easily. So there's the hope that general concepts like depth or 3D geometry or things like this will emerge naturally from the ability to predict how the world changes when, because the world is being the world or because we act on it. So that's the basic motivation for this idea of predictive learning or imputative learning or whatever you want to call it. And there's some indication that that's what animals and humans do by, we build models of the world by observation, mostly by observation, with very little interaction with the world, because interacting with the world is dangerous. It costs energy, and you can't do it too many times because, the real world runs at its own pace. And so, so the question is, how do we do this with machines? And currently, we don't. Okay, so that's, in my opinion, the biggest obstacles to making real progress in AI is having machines that have the ability of learning models of the world, particularly predictive models of the world, from observation. And there's, a lot of evidence that I showed yesterday that babies do this, learning basic concepts like intuitive physics, gravity, inertia, stability, etc., in the first few months of life, where babies basically don't really interact with the world very much. I mean, they're kind of, in their beds and things, and they just observe things, essentially. And they learn a huge amount of background knowledge about the world, much more than any machine that we've built so far. So there is, a couple things that people like Jeff Hinton have been saying for 30 years, that we need unsupervised learning. We need machines to be able to be trained to predict everything from everything, because that's the only way we can train very, very large machines with so many parameters, right? The argument is the brain has about 10 to the 14 synapses. We live for about 10 to the 9 seconds, so we have a lot more parameters than data. This motivates the idea that we must do a lot of unsupervised learning, since the perceptual input, including proprioception, is the only place where we can get 10 to the 5 dimension of constraints per second. And he's been saying this for 30 years. For the first 10 years of that, I didn't believe him, and kind of changed my mind 20 years ago or so. And so if you measure in terms of the amount of information you ask the machine to predict, this mode of learning, of predictive learning, predicting everything from everything, essentially, predicting the future, etc., there is a huge amount of information that you ask the machine to predict. And what that means is that you can learn many more things with many fewer samples or trials or interactions with the world or real-time seconds or any way you want to measure it, right? So this is the main mode in which you can learn how the world works. Supervised learning is just, plays a minor role, because you're only given a small amount of information about the world in supervised learning. You're just given the label of an object or something. And that has to come from an intelligent agent, so necessarily it's not something that's available in large quantity. And reinforcement learning is the scenario in which you're only being told whether the action you just took was good or bad, or whether a sequence of action you took over the last hour was good or bad. You just lost a game of chess. What mistake did you make an hour ago, right? Not easy, right? So necessarily, AI will not derive purely from reinforcement learning, not purely from supervised learning, even if we spend a huge amount of resources collecting data. It's going to have to come from this. That's the only way machines are going to acquire common sense, which led to this obnoxious picture of if intelligence is a cake, and supervised learning is a genoise, and supervised learning the icing, and reinforcement learning the cherry on the cake. And then I realized that I used the picture of a Black Forest cake, which happens to have cherries inside, but So we're in a bit of the same situation as physicists because you ask physicists, what's the universe made of? And he says, well, all the matter that we know about, that's 5% of the energy in the universe. The other 95%, we have no idea what it is. Here's the same thing. We know how to do this. We know how to make the icing. We have no idea how to make the cake itself. So this is the dark energy of machine learning. Well, actually, the black part is dark energy, and the white part is dark matter. Right, and the whole thing is 95%. So RL works well for games. It works well if you can run the world faster than real time, or if you can run it in parallel on 1,000 machines. But in reality, you need a model of the world, and this argument that you need a model of the world was actually formulated by one of the grandfathers of reinforcement learning, Rich Sutton, who was proposing an architecture to do just that. He said, you need the common sense idea that planning is trying things in your head using an internal model of the world, and that if you try things in the real world, you're kind of making life more difficult for yourself. So there's this idea somehow that you would have a predictor, kind of a model of the world, a predictive model of the world, and you would use this to plan ahead, which is a very traditional, classical way to do optimal control for optimal control theorists. And this model of the world is something that you train by observation, essentially. Okay, so the next revolution in AI will not be supervised. In fact, it's already the case that a lot of people are working on unsupervised running for different purpose. But let me go ahead into the architecture of an AI system. So an AI system, an autonomous AI system would be kind of something like this. It has an agent that produces actions that act on the world. The world responds with percepts. They go to a perception module. We know how to build this, at least in supervised mode. And the agent, kind of changes its state and then produces action again. And what the agent is trying to do is minimize the value computed by an objective, hardwired objective function here. Okay, so internal to the system, there is an objective function that drives the behavior of the agent, and everything the agent does is directed towards minimizing the average expected value of this objective, essentially. So we have a module like this in our brains. And at the bottom of our brain, we have something that computes whether we're happy or not, whether we're comfortable or not. And where we're unhappy, uncomfortable, scared, hungry, whatever, it drives our behavior. Right? It drives us to do something about it. So that's intrinsic motivation, if you want. So we're going to have to, if we build autonomous machines, they're going to have something like this. And it's going to drive the behavior. And we're going to have to design this or train it in such a way that those machines behave properly. Inside of the agent, if the agent is to be intelligent, it has to have some way of simulating the world, of predicting what the consequence of its actions are going to be, or predicting what the world is going to do, even if it doesn't take any particular action. And it's going to have like a little kind of simulated version of itself, producing action proposals in this world simulator. And then the world is going to generate, predicted percepts, and then this actor is going to, dream about its own state of mind, and then feed this to a critic, which is basically a predictor for the long-term expected value of this objective. So this guy anticipates what the value of this objective is going to be. So for example, if this guy, if after a few simulations here, you predict I'm going to run off a cliff with my self-driving car, this critic here is going to, shoot up and say, hang on, this is not going to, you're not going to be happy about this. And the simulator, if you keep running your internal mental model, is going to tell you you're going to run off a cliff. So in a particular episode, you get a state of the world through the perception system, and then you run through your world simulator a sequence of actions, and you figure out a sequence of action that optimizes the output of the critic, and then you take the first action, and then see what the world says, and do that again. We know how to build those two modules. We don't know how to build this world simulator, so that's the problem. How do we build predictive models of the world? So there were some experiments that were done a few years ago by some colleagues at Facebook, Adam Lehrer, Sam Gross, and Rob Fergus, which they published at ICML in 2016, of kind of learning intuitive physics. So a very simple, situation where you show a system a stack of cubes, and you ask it predict what is going to happen to the stack of cubes. And of course, this is in a a game engine, so you can run the game engine and see what happens. So here the stack of cube kind of falls. And this is what the neural net produces. That's a prediction it produces. And what I want you to notice is that those predictions are kind of fuzzy a little bit, right? And the reason they're fuzzy is because it can't predict exactly what's going to happen. You know, it's got some idea that the yellow cube here is going to fall that way, but not, you know, not precisely. So you get those fuzzy predictions. And this is a hint at the main problem that we have to solve, and it's to some extent a mathematical problem with training predictive models, which is that the world is not entirely predictable. So I'm going to skip this. So why is the world not entirely predictable? So one reason is, you know, there are things, you know, the limitation of our perceptual system says that, you know, if I put this in my hand and I let it go, you know that it's going to fall in one direction, but you can't really tell which direction, you know, because, you know, you're too far away and I can move my hand and all that stuff, right? So the world is not entirely predictable. What you have are dependencies between variables. You're going to observe different variables and the dependencies between them, but you can't exactly predict the value of a variable. So let's imagine a world consists of 2 pixels, y1 and y2, or 2 variables. And this is our world. We observe this universe here. We can predict to some extent the value of y2 from y1, particularly if it's in this, if y1 is in this region. But if we know the value of y2, we have a hard time predicting the value of y1 because, you know, there are 2 of them. Or here there is a whole bunch, right? So if we want to predict y1 from y2 or y2 from y1, predict everything from everything else, we need a way of representing sets, not single points, but sets or manifolds or distributions, right? And the way to do this is perhaps to train a machine to learn a contrast function that is going to take low values on things that are actually observed and larger values on things that are not observed. So think about this as like an energy function in physics, right? The stuff that actually happens are kind of, you know, the minimum of the energy, and things that don't happen are higher energy, things like that. A contrast function that really indicates what's possible from what's not possible. And there are kind of people over the years have worked on a whole bunch of different ways to train those contrast functions, or energy functions. It's called energy-based models, or probabilistic models. And I'm not going to go through any of those, because there is one in particular that I think is very interesting, adversarial training, which I mentioned yesterday quickly. So it's this idea that you want to train a predictor, but you know that the prediction cannot be a single point, but a whole set of possible predictions, but you don't know which one. So you're going to make the system predict a single point, but you're going to give it access to a source of random vectors. And those random vectors are going to be used to parameterize which point on a manifold of possibilities or a set of possible prediction is going to be generated at any one point. And so, you know, it could be that the machine, you know, predicts that the pen is going to fall to the back and the left, but what actually occurs in the world is that the pen goes to the back. And you don't want to punish the machine for making the wrong prediction because, you know, it's part of the set of potential futures. And so you'd like to train the machine with an objective function that tells it if you go away from this manifold, you pay a price, but if you stay on it, it's okay. And of course, we have no way of characterizing the surface other than by training another neural net to tell us whether we are on it or not. And that's this contrast function I was telling you about, right? So this is the contrast function, and it's going to be computed by this neural net called a discriminator, which is going to be fed real data and fake data produced by a generator. And it's going to train itself to give low energy to the real data and high energy to the fake data, leading to something like this. So by feeding it fake data and real data and training it to discriminate between the two, it's going to compute a surface of this type. It's a high-dimensional surface, okay? This could be images, right? Entire images. Now, we're going to do something devious now, which is why it's called adversarial training. This generator is going to train itself to produce fake data that this guy can't tell are fake. And so it's going to try to move its predictions, its green dots, towards the blue points. And it can do this by getting the gradient of the output of the discriminator with respect to its input. So you can think of the discriminator as a trainable objective function that the generator uses to train itself to produce points on the manifold of possible futures. And eventually you get to this thing where this guy produces good predictions, and this guy can tell the difference between real and fake. And there is an enormous amount of work on this over the last 2 or 3 years. There's still no good recipe that makes it work in every case, unfortunately. There's all kinds of ideas based on interesting mathematical concepts like variational inference or minimal transport, optimal transport, I should say, or, Wasserstein distance, things like that. So there is, a lot of kind of mathematical puzzles in there, like someone who can find kind of a well-principled way of building and training those systems with good objective functions, I think is going to win a big prize because there's a huge amount of interest in it. And the reason there is interest is that when you manage to make them work, they actually produce amazing results. They can generate faces, and they get sort of parametrization of the face space that allows you to do face arithmetic, right? So you take the image of this guy in the latent space of the vectors that are used to produce this space. You subtract the vector corresponding to this guy, you add the vector corresponding to this lady, and when you regenerate an image, you get a lady with glasses, right? So man with glasses minus man without glasses plus woman equals woman with glasses. That's pretty amazing, isn't it? And you apply this to all kinds of different domains, and it just works. You can do this with text and all kinds of stuff. It's pretty amazing. You can have it generate all kinds of weird images. You can use it to do video prediction, which I showed yesterday. So this is if you use traditional supervised learning criteria, like least square, and this is if you use this adversarial training type criterion to train. It can invent what a piece of an apartment looks like, completes those bookcases and couches and various other places in apartments, and it can predict what people are going to do on the streets, or cars are going to do on the streets. Motorbikes are going to cross the street, pedestrians are going to continue crossing the street. So the last few frames of each segment here is predicted by the machine. The scenery is going to keep going through, etc. So that's kind of useful if you want to build machines. Okay, I'm out of time, so I'm going to skip to a bit of a punchline. I didn't intend to talk about this. Okay, this is about the impact of deep learning on AI. So one thing that's interesting is that we don't understand all the theory about deep learning, which is one of the reasons why we have this workshop, by the way. So we get interest from people who understand theory, and we kind of explain what the problems are, and hopefully kind of spur collaborations. And one of my big motivations for coming to IPAM every so often is exactly that. It's because I think there is a lot of theoretical and mathematical puzzles behind those things, some of which I mentioned. So there are people in the machine learning community who have been critical of deep learning because of the fact that the theory we have is a little weak. But then I kind of reflected on this a little bit and thought about how technology and science progresses. And the invention of the telescope and the microscope preceded optics. The invention of the steam engine preceded and motivated thermodynamics. The invention of the airplanes essentially preceded aerodynamics, not entirely, but we understood a lot more about aerodynamics after we started inventing airplanes, because there was a huge motivation to really understand, and certainly for stability and stuff like that. The invention of calculators, led to computer science and the theory of computing. There was no interest in this before we could build computers, essentially. And telecommunication motivated the invention of information theory. So a lot of conceptual advances, mathematical science conceptual advances or theoretical advances come from the invention of artifacts that need to be explained or optimized or fine-tuned. And so my question, a scientific quest is, what is the equivalent of thermodynamics for intelligence, right? Is it the case that the invention of intelligent or semi-intelligent machine will lead to a new science of intelligence? And I hope that's the case. We haven't come up with this science yet. Computer science is kind of just an embryo of it a little bit. Is there an underlying principle that underlies the functioning of not just intelligent machines, but human intelligence, animal intelligence, etc.? That's a big question. Let's see. I'm gonna my last slide is about a completely different question that has nothing to do with technology or nothing to do with, scientists, let's say. But it's a question I get asked a lot when I talk to the public, which is that, is it the case that AI is going to take our job, first of all? And second of all, is going to make us useless and, is going to change our evaluation of ourselves. And my reaction to this, and after talking to a bunch of economists, I've been hanging out with economists lately, is the following. You can buy a Blu-ray player for $47. A Blu-ray player is an incredibly sophisticated piece of technology. It's very, 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 very difficult to build. It involves technologies that was developed only in the last 10 years, H.264 compression, blue laser, whatever, or the last 20 years, let's say. It's built by robots, which means, it's you can buy it for $47. Now, if you want to buy a handmade ceramic bowl, it's 10,000 years old technology, but it's handmade, it's going to cost you $500. And the difference is the human experience, right? So things that have true human experience in them cost a lot more than things that you can manufacture by machine. So automation is going to make the price of a lot of material things go down, but there are other things whose value is going to go up, and it's true human experience. For the same reason that you can download a recording of Die Zauberflöte by Mozart for $6, but if you want to go to the opera in New York, the price go up to $800. I mean, you can get cheaper, but the more expensive one at $800, that means there are people who pay that price to go to a performance of Die Zauberflöte, and that's just the human experience, So I think it's going to change the value we attribute to things, but it's not going to diminish the value of humanity. In fact, it's going to be the opposite. Thank you very much.
So let me open it up to questions. Are there any questions for Yann?
Thank you for the talk. So I'm wondering whether you think it's true that all the problems can be put into two buckets, where in the first bucket you have problems where, like for example, 2 billion images per day, where you can use deep learning methods. And then in the second bucket, you have problems from like pilot studies where you have thousands and thousands of biomarkers measured on patients, measured on, for example, a few hundred patients, where it's just currently impossible to use deep learning on those data sets. So my first question is whether you think it's true that problems can be dichotomized into two categories. And the second question, if so, do you think there will be a convergence of the two buckets into like a single category where we somehow manage to better, regularize deep learning methods to work on smaller studies?
Yeah, so I think it's not a limitation of deep learning, it's a limitation of supervised running. So pure supervised running requires a lot of samples. But it's already the case, for example, there is a service within Facebook, for internal purpose, where an object recognition system, an image recognition system was trained with tons and tons of images for all kinds of different things. In fact, some of them now are trained not even with human-provided labels, or at least not precise labels, but with hashtags that people can randomly type. Okay, so that's enough to train a system to produce good feature representations for an image. And then with just a few hundred samples of any new category, you can retrain a small classifier on top of these features to do any kind of task. So that's called transfer learning. I think if you generalize this, there's a problem, for example, that people face right now where for translation, you can train a large neural net to do translation between, let's say, English and French or English and German, because there's tons of data. But if you want to translate, Swahili into Hebrew, there's not a lot of data sets for that. And so one idea that Google has been working on, Facebook has been working on, etc., is you share a lot of resources between the various translators between all pairs. So instead of having a completely separate translator between every pair of language, you have an encoder that takes English, an encoder that takes German, and one that takes French, that takes Swahili, and whatever they speak in Java, and have them produce a common internal representation for meaning, and then you have a bunch of decoders for every language. So even languages for which you have a very small amount of training data, you can sort of take advantage of the general structure of language for them to kind of learn something. So there's a lot of things like this. I think ultimately what's going to happen is that there's going to be more generic models that have learned the general structure of DNA, let's say, or language or whatever, mostly in an unsupervised manner, and then supervised learning would be a little piece on top of it, the icing on the cake, essentially. But most learning will be unsupervised.
Okay, thanks for the talk. I have a question about predicting the future that you mentioned. One example that you presented was this adversarial training, but so what common sense is telling me is that when we look at the picture that you showed, we had cake, we had candle. So do you think maybe is it a better approach that we use some sort of memory networks for predicting the future instead of like using adversarial training? And by using memory network, I mean using some sort of side information about the scene or the picture that we care about.
Well, those are orthogonal concepts. You can use adversarial training to train a memory network, right? There's nothing wrong with that. To some extent, you could think of those video prediction systems as having some memory. They look at the past frames and they store a representation of the past as kind of a hidden state, and then they use that to predict the future. It's not a memory. It's not an accessible scratchpad memory like the memory network, but because it's kind of a fixed structure. But there's no reason why we couldn't use a memory network for this. In fact, there's some work on this, which I skipped over, for dialogue systems, where you want to train a system to hold a dialogue with a person, talking about movies or restaurants or something like this. And the system has to keep track of what was talked about before, perhaps using a memory network. But it needs to be able to predict what the person is going to respond, to be able to kind of hold a dialogue that makes some sense. So this idea of prediction is orthogonal to the idea of memory. You can combine the two.
Oh, hello. Thanks for the talk. It was really interesting. So you mentioned the importance of having the world simulator. So I was wondering what you thought about causality, because causality is very important in physics, but machine learning is just correlative. And also, a related thing that came to mind was the idea from Jeff Hawkins that time is very important. So having, for instance, in the brain, you have sequences of spikes that are kind of propagating, and he believes that time is important. So I was wondering, what do you think about causality and having time, a notion, of time inside it?
Right. So causality is, the establishment of causal relationship is really important. This is not something that humans are particularly good at, by the way. So, for example, if you ask young kids, what is the cause of wind? A common answer, not prevalent, but common answer is the wind is caused by the leaves in the trees, right? The leaves in the trees move and they kind of agitate the air, and that's what causes wind. The causality now is backwards, right? So we're not very good at this ourselves. It's very easy to get fooled. In fact, it's not entirely clear that, from the point of view of microphysics, that there is such a thing as causality, because every equations of physics are reversible, time reversible, so it's not clear what it means. But there are people who work on causality because it's obviously very important. If you want to be able to have a model of the world that tells you that if you do a particular action, a particular result will occur, then you need to establish some sort of causal relationship, right? So there was actually a talk yesterday at the workshop about establishment of kind of causal relationships in models. It's very important if you want to build explanatory models, not just predictive models, but explanatory models. For example, you observe, I don't know, DNA expression, and you want to figure out what is the regulation network of the genes, then that's sort of an inference of a causal model, if you want. So yeah, it's very important. There's a lot of people at Facebook working on it who are very interested in this. Now the second question, what is the importance of time? So of course, one type of prediction is temporal prediction, predict the future from the present and the past. So in that sense, if you believe that prediction is an essential component of unsupervised learning and the acquisition of common sense, then time, of course, is important. But it's not the only type of prediction, right? You can predict what my right profile looks like only looking at my left profile. Well, the other way around. What my left profile looks like only looking at my right profile. Because you know that faces are more or less symmetric, things like that. I mean, there's a lot of things you can predict that are not necessarily sequential in time. You kind of know more or less, even if you've never seen it, what this lectern looks like in what you don't see. So that's the idea of prediction in general, and temporal prediction is just a special case. So I don't attribute any kind of particular quality to temporal prediction over others.
I had a question about the world simulator, and if there were a practical case where people have built robots or AI systems that observe the world and see how others or other things in the world act on the world,
yeah.
And then they themselves, like babies do. My children, they see me do something, and then they try it themselves, but they first watch other people do it.
Absolutely. So I should say, this idea of having a simulator of the system you're trying to control is very classical in optimal control, as I said. So a lot of robotics, classical robotics, actually consist in actually writing by hand the dynamical equations of the robots, and then by gradient descent and various other techniques, kind of figure out a sequence of commands to achieve a particular goal. Okay, this is classical robotics. Generally, that model is not learned. It's handcrafted. There's a few parameters that are identified, but generally it's just handcrafted. So the next step is, can you learn the model from some structure, but not a huge amount? So that's called systems identification. And then the next step is, can you kind of learn the model from scratch, not having much a priori structure about what the model looks like? And that's what we have a hard time doing, particularly in the presence of uncertainty. Now, back to more directly to your question, there's a whole field of machine learning called inverse reinforcement learning or imitation learning, which is basically exactly what you're talking about, where you observe people going through particular trajectories, for example, or doing particular things. And then the way you train this is a bit like adversarial training, where the machine internally has a kind of one of those contrast functions that is going to give low cost to things that it observes from other people and high cost to things it doesn't observe or things that it produces itself. And then it's going to learn to produce behavior that looks like the person is looking at through this function. It's very similar to adversarial training. In fact, it precedes adversarial training to some extent. So yeah, it's a whole subfield, imitation learning.
All right, so thank you so much, everybody, and let's give Yann one big round of applause again. Thank you.